7:30, and everybody be ready. And come 9 o'clock, well, something's not working. The cameras aren't working. The tape recorders aren't working. Something's not working. So we go around, and by 3 or 4 o'clock, we'd be lucky to get it going. We'll come back tomorrow and try again. Hopefully, we're not in that mode here.
Yeah.
They weren't even moonshots at that point. First suborbital and orbital flights. The astronauts sat there in the cockpit for hours.
We're ready to go. So whoever wants to, get in there. Okay, yeah.
I was.
And we use the microphone so that we can hear. You want to go red? Let me just. Okay.
All right. Do we have a good sound level here?
Yeah.
Okay.
And they'll be able to hear you through that. That's just the rest.
Right. Good morning. My name is Tony Van Kuren. I'm with the Research Division of the California Air Resources Board, and I'd like to welcome you to this Chairman's Seminar. Today's topic is going to be the effects of urban aerosols on precipitation in California and Israel. Our speaker is Dr. William Woodley, who is an expert on clouds, cloud processes, and aerosols effects on clouds, and he'll be reporting on work that was done cooperatively with Daniel Rosenfeld and his group at the Hebrew University in Jerusalem. I don't want to take any more of our time since we're running a bit late, so Dr. Woodley.
Thank you, Tony. It's really a pleasure being here today. I love all this technology that, excuse me, that apparently is going to work. I've had some real nightmares with PowerPoint, but everything looks really great. Well, I'm going to talk about urban-induced changes in precipitation. Let's approach this as though it were a court case. I present all the evidence, and then each of you reach your own conclusions. Is it likely this is taking place, and if so, or is it not? And the way I look at it, excuse me, with the frog in my throat. The way I look at it is a study of this kind has to involve physics, observations, physical observations, and statistics. Neither tool is sufficient by itself to convince you, the jury, so to speak, that in fact this is taking place. So I don't think the statistical arguments, which I view rather strong, suffice, nor will the physical observations. But in their totality, I'm obviously of the view that in fact aerosols, specifically cloud condensation nuclei of sizes much less than 1 micron, are detrimental to the precipitation in California, specifically the precipitation in the mountains, the Sierra Nevadas and the mountains east of Los Angeles and San Diego. The real brains on this is Rosenfeld. He's a very talented scientist. I worked with him under my company, Woodley Weather Consultants, for darn near 25 years. He's one of the most talented people I've ever worked with, probably the most talented. I want to make sure not only am I going to say that, I'm going to introduce him. There he is. To make sure that you don't get confused, and this is the real brains behind the operation. In this particular area, I've made some contributions, but Rosenfeld's the real brains of it. The statistical aspect of this is that of Mr. Amir Javadi, who's a graduate student, PhD candidate at the Hebrew University in Jerusalem, Israel. Slave labor, so to speak. If any of you have been through that, talented graduate students are worth their weight in gold as far as I'm concerned, and he's quite valuable of himself. Now I'm going to talk about the effect of added cloud condensation nuclei and put it in very simplistic terms. The aerosols determine the nature of the clouds that you have. I used to be a big dynamics person, and now the aerosols will take care of themselves. As I get older and perhaps wiser, I realize the aerosols are incredibly important. You guys could have told me that with what you do here in California. And the more I'm into it, the more important it appears that they are. And you'll see up in the upper right there something we call industrial pollution tracts over Manitoba, Canada. I'll get to that in a minute. And down here on the lower right, you see ship tracks off the Washington coast. And this is the ship tracks is viewed at 3.7 microns in the radiation. So the whole idea is that an excess of the wrong size of cloud condensation nuclei slow down, make it more difficult for the water in the cloud to be partitioned or ultimately grow into raindrop sizes. They all stay small, and you ruin the precipitation process. In its simplistic terms, that's what we're talking about. Now, we're not operating blind here. There's about 4 or 5 years of publications on this very subject. One by Rosenfeld that appeared in the Geophysical Research Letters dealt with the effect of these monstrous fires in '97 in Malaysia and Indonesia. It's documented unequivocally that the aerosols, the smoke in that fire, contained cloud condensation nuclei, and that was highly detrimental to the precipitation. Now, before I get questions on this, if those of you are well versed in the past, I'm going to be talking today about relatively shallow convective clouds that don't, and of rather short lives individually. I'm not talking, I could, but I'm not talking about deep cumulonimbus convection, let's say in the 2/3 of the United States. So cloud condensation nuclei, like anything else in life, some is great. It's too much of a good thing sometimes that causes you all the grief. And in this case here, the excess of CCN in this environment and in Israel, and in fact Australia is going to come under some discussion here. It's not good. However, if you were to go to areas like Missouri and Alabama and East Texas, etc., where you have highly maritime conditions where it rains very readily, would you believe that our modeling efforts, we do a lot of modeling, as do you, individual cloud modeling, 2D, explicit microphysics, etc., show, as best models can, that polluted air is actually good for the enhancement of precipitation. Now you say, no, wait a second, you're contradicting yourself. The effect of CCN in high quantities in this environment makes the precipitation process inefficient, indeed. But what it does is it allows the cloud to churn and generate and get larger without the disruptive effects of downdrafts that are associated with precipitation. So the models, and by the way, I'm not a modeler, much as Tony says he's not a modeler, but we're pretty good observationalists, and we always insist, I think models are the most wonderful things that's come, but they must be validated. If your model doesn't measure up to the real world, I ain't interested. But now we've got models that in fact do. So in my humility, I bow to the modelers and say this is fabulous work. So what they show in the east part of the United States, and this is it slows down the precipitation process, allows it to grow, you don't get the downdraft, and allows the things to organize into large, massive systems in some cases. And you get far more precipitation after, let's say, an hour or two from the system, in the polluted system, than you do in the one where you've got an excess of CCN. That's not going to happen, modeling-wise, in the environment here where you claim Mediterranean climate. What do we call this climate? I'm a native of the state, Mediterranean climate, whatever. But the clouds here are not receptive to excesses of cloud condensation nuclei. Now here's an intriguing picture. 10,000 words in this picture here. I'll limit my words, hopefully. But this is Australia. Southeastern corner of Australia. This is Adelaide here. And you say, where did we get colored clouds, Woodley? You know, what planet are you on? Oh, this is due to the cleverness of Rosenfeld. And let's see how well I can explain it, because frankly, it's a subject of 1 or 2 seminars. So let me give it a shot. As you undoubtedly know, if you go back to this picture right here, the way things appear is a function of where you are in the radiative spectrum. And we've known for some time that at 3.7 microns, when you have effluent from fires, or in this case from ships, the stacks of ships, what it does is the CCN in there, it makes for smaller drops, much smaller drops, and those smaller drops are much more visible in the 3.7 micron channel. So this is an admiral's nightmare. Literally, this is an admiral's nightmare, because you keep track of all the ships. And this is not the pollution. I want you to understand, when everything you see here, you're not looking at pollution per se, you're looking at the manifestation of the pollution in the clouds. So you're looking at a cloud deck, this is all overcast. but these enhanced lines, those are the tracks of ships at 3.7 microns. Now, I don't know what the Navy does. I don't work for the Navy. But I'll bet you they're working on a program to somehow negate this kind of effluent from ships. I don't say these are Navy ships. These are, ships conducting commerce over the Northeast Pacific. Back to this picture. Now, the cleverness of Rosenfeld. As you know, Nakajima and King have developed a radiative model which allows you to characterize the effective radius of a cloud. Effective radius is just a measure of the totality of the drop populations. I mean, all the drops are that size. It's like median volume diameter and other measures. We chose the effective radius, Nakajima and King radiative model, and they can give you the effective radius of the surface of an individual cloud using the 3.7 micron channel. Now, what Rosenfeld did, made the assumption that if you look at a field of clouds, like this or whatever, look at all the clouds, you're going to get clouds in various stages of development. Some little guys, some big guys, some monsters, and everything else. These aren't monsters here because this is Australia. He made the assumption, the claim, that one could take all the observations, put them together in one image, polar orbiter image, and claim it's one cloud, and present the data in percentiles, 10% up to 50% to 90%, percentiles, as though it's one cloud. Now, I was privy to the reviews of his paper way back, gosh, it was published in the Bull American Meteorological Society in Rosenfeld and Lenski in 1998. I saw the reviews. And some erudite, obviously a erudite meteorologist said the problem with Rosenfeld, he doesn't know cloud physics. Reject the paper. Fortunately, the other two reviewers had a different point of view, and it was published, and you'll be amazed at what's transpired from that initial point. Here's a case, and we all do this. I'm 61 years old. I try not to think in the box. People that think outside the box, most of the time they're probably wrong, and they just drive you up the wall. But once in a while, people that think outside the box have something really important to say to us. And here's a classic example, thinking outside the box. So I will show you he's able to generate profiles of effective radius of a cloud as a function of temperature or height, if you relate temperature to height from a sounding. Then, in order to make it easy for us to look at, he colorized them. Now, how did he do that? I just got to tell you the story. If you went to Home Depot or wherever you buy paint these days, and you want to give in color, that's what he's done here. In the visible, if a cloud in the visible is very bright, it gets very red. If it isn't bright, it's no red. If a cloud is very cold, no blue. If it's warm, it's blue. That's why these oceans are blue here. Likewise, in the particle sizes, 3.7 micron channel, there, if the particles are small, they're green. And if they're big, they're not green. There's no green. Now I can drive you nuts here on your pads figuring out how these colors came about. So he puts them all together, and this is what you get. So therefore, a cumulonimbus cloud, very cold, no blue. Larger particles, ice crystals and everything else, no green. And very, very bright, red. So a cumulonimbus anvil typically looks like red. These are not cumulonimbus, these are magenta. But now, with this as background, this is Australia, which is more of a pristine continent than we are here in California, United States. So let's not wave our fingers at the Aussies. Although I am going to have some negative things to say about some of them momentarily, if they're listening. Here you have yellow-green areas, and you can go through your color scheme. Suffice it to say that these are areas or manifestations of pollution in Australia. And you can actually go back and trace it back to individual stacks in this case. Now, the Aussies, unlike California, do a lot of coal-fired power plants. And that's their big bugaboo. So, here is a quantification of a small part of that picture in the colors. And I'll go ahead and then come back. now this is only, these are polar orbiters. One picture. This is an analysis of one picture. We are still drooling at the prospect later on of geosynchronous multispectral imagery. The Europeans have it now in Meteosat. We don't have it yet in America. So, but this is just an individual look at one time as the polar orbiter moves over. And in this case here, areas 1, 2, and 3, he's actually generated effective radius plots as a function of temperature. And this is for area 2, area 1, and 3. And this is the 15th percentile, the median, and the 85th percentile. Let's look at the solid part of the curve. They're different. They're very different. They know from the studies that a cloud has to have a drop size of roughly, effective radius of about 14 microns to have precipitation. So the claim is, from this analysis, is that clouds in area 1 and 3 are precipitating. But in 2, which is far away, the average here is at best 10 microns, it's not precipitating according to the Rosenfeld method. Now this is imagery from the TRIM satellite, which is launched jointly by the United States and Japan. And going back here, here's a blow-up of that. And on this satellite, as you probably know, there's a radar, a downward-looking radar that estimates precipitation. The white stipple are echoes, radar echoes. Independent measure, has nothing to do with the Rosenfeld method. This is just a radar measurement. It's raining in area 3, substantially, and in area 1, there's nothing in area 2. You can look at the other imagery to know the clouds are of the same height and depth and everything else. It's just not precipitating in area 2 at all. Now, an interesting story is that Rosenfeld went down and gave a seminar in Australia about 3 years ago. Maybe it was 4 years ago. Unlike California, where you've had a gradual increase of precipitation over the 20th century, which is masking the negative effects of pollution. I will show that in a minute. In Australia, they have a real serious problem. Very serious problem with water. And the problem is most serious not at the coast, but inland, in the catchment areas. The snowy mountains are not snowy anymore. Now, the snowy mountains, I'd have to go to back to the other picture, but this picture, in this area here, Melbourne is down here. They have a whole forest of coal-fired power plants. What do coal-fired power plants produce, among things? They produce cloud condensation nuclei of the wrong size, well less than a micron, tenths of a micron in size. And there is a manifestation of what it's doing to the precipitation. It isn't precipitating. And these are relatively shallow clouds, as they are in California. And so it's extremely detrimental. The CSIRO, which is a prestigious group in Australia, good scientists, is so stuck in its ways, though, they weren't going to listen to it. Do you know how they countered Rosenfeld's arguments and presentation? They trashed their data. They said the data that we provided you are not good enough to do what you did with the data. And that end of story. It's over with. So ultimately, probably when somebody gets enlightened within their ranks, they're going to address this. But meanwhile, they're totally and utterly blind to their predicament and not inclined to even discuss it. Here's more examples of plots with effective radius. In the observational area now, here you have plots in India, Australia, Thailand, the Amazon, under smoking condition, Israel dust. On these solid curves here, notice they're all, until you get to about -5 to 10, they're all effective radii are less than 10 microns. In pristine conditions, same areas, look at what it is. The whole doggone soundings, the effective radius is greater than 15 microns all the way up. Very, very big differences. It's a function of how much pollutants are in the air. Now, this is some work that we quoted from the folks at DRI up the hill and over the hill here. Boris, I probably didn't pronounce his name right, and Lowenthal et al. They did some really great work. And this is some work that they've done, very painstaking work they've done in the laboratory east of Steamboat Springs, Colorado. And they show that as little as 1 microgram per cubic meter of sulfates in the air, in this one case, that appear to be comparable otherwise, you have a rain rate that's, what is that? 0.02 versus, this is the polluted case, 0.02 millimeters per hour as opposed to 0.38. So indications are, and they looked at it, and this makes sense. When you have the polluted case, you don't rime as well. The drops are so small, you don't develop ice of a size sufficient to do much riming, and therefore you have a deficiency in rhyming, and therefore precipitation doesn't develop as readily. In fact, if somebody were a nut that lived in Sierras, for example, making the same argument, you'd have to argue that in the polluted areas you don't have as big, humongous snowflakes as you might have seen elsewhere in the world. You tend to have smaller snowflakes. That's what you should have. This is the kind of work that is needed. My compliments to them. They ought to do more of it, and I presume that's what they're going to do. But again, what have we had so far? We've had the Rosenfeld methodology, which says pollution affects the effective radius. We've had a satellite pass over with a radar that says there's a deficiency. It's not raining where it's polluted. And now we have this observation. Now this is in Colorado of when they look at the sulfates and the precipitation and infer these differences. Okay. Now we're eventually going to get into some statistical presentation. Now the purpose of the study is determine whether there's deficiency in precipitation downwind of major urban areas, and under what conditions the pollution effects are most effective. I'll let you read some of this as I talk. This is really, how did we get into this? How did they get into that? Well, as a consequence of Australia was the first venture into this area, and the Aussies just ignored it. But the argument was, well, if this happens in Australia, it might well happen in California, or in Israel. But if you're arguing cloud condensation nuclei, and you don't have much in the way of coal-fired power plants, Tony enlightened me prior to the talk, and if it does take place, what's the source of the cloud condensation nuclei? The first thing that would come out of my mouth would be diesel engines, which we know produce large quantities of that. But that's really your bailiwick, not mine. I'm not going to be telling you your business. I'm going to show you, I think, that there's a problem, and then you're going to enlighten me, hopefully at the end of this, as to what its likely cause might be and how we might jointly look at it. All right. Now, Rosenfeld has had an association with NASA. NASA loves to brag about their things. They're pretty smart in touting their own stuff. This is an animation that they made up. I'll just show it to you. This is the so-called clean condition. It's compressed urban areas, mountains. This could well be Salt Lake City or, I guess, compressed Sierras, where you get the precipitation, most of it on the windward slopes, on the crest, and then less downwind. And then if you go to a situation where you've got a polluted circumstance, and this is only for visual purposes because the air in California visually has been cleaned up dramatically since I've been in the state. So that's only there for viewing purposes. But the argument there is and we'll show is that you're getting less precipitation on the windward slope, a little less on the crest, and a little more actually on the other side, on the east side of the Sierra. But the net effect is a major loss of precipitation. These are some of the stations, and there's hundreds of these. I'm going to try not to bury you with all this stuff. These are the types of things we're going to be looking at, stations in California. And here's another physical measurement. When Rosenfeld and I attended the American Geophysical Union meeting in San Francisco this year, to help you understand my colleague and good friend, he's sitting on the right side of the aircraft with his camera. This is from a satellite, you'll see, but he's taking pictures. And he notes that we're in the cold sector of a cyclone. You know how things work in California. You have the prefrontal storm, thick clouds, southerly winds, southeasterly winds along the Sierra, front passes, cold air aloft, overturning, and shallow convection. This is on the cold side of the cyclone, this picture. And I'm ahead of myself, but we'll show this is the regime where the effect is largest. So he's taking some pictures. There's his route of flight. He's taking some pictures. I'm going to go. That's Mono Lake on the east slope. Go back here. And then what he did with his army of talented students in Israel, he calls them up and says, "Get me that image, and let's do my analysis on the image." So this is an analysis about a month old that he did in about a day or two between when he arrived in Israel and when he made his presentation to the people. So, that gives you some idea. And, of course, I've worked with him for like 20, 25 years, and these kind of things that are possible. So you see all these areas. We're going to take a quick look at the effective radius in these areas that happen to be in the Sierra. Here's some pictures. Again, Mono Lake. This is right over the crest of the Sierras, looking back at the Sierras. I'm probably in somebody's way here. And then the picture looking back at San Francisco. The visibility is not good, you'll notice that. And if you look, if you start in Area 3, now that you're comfortable here, you see that the interface of green and yellow is essentially the 50th percentile median. And you can see there the curves are already at 15 microns, 14 microns and greater, so it's precipitating there. And then as you come south, Area 5, here's San Francisco. This we view as a relatively pristine area. As it comes south, all the way down to Area 9. Now, Area 9 is directly east of San Francisco. The westerly flow, cold air, relatively shallow clouds. The effective radius here, between let's 0 and -10, has moved to smaller effective radii. Again, this doesn't prove pollution is causal. Look at Area 9 again and work ourselves farther south. As you come south of the Bay Area, the lines move back over. Here, Area 16 is very, very large effective radius relative to others, and Area 16 happens to be, in this case, east of San Luis Obispo, or that general area there. It's in the Sierra Nevada. And you work south into keep coming south, get to Area 20, you're getting into more population, and when you get to 24, which is immediately downwind of Los Angeles, look where the effective radius is. Less than 10 microns. Less than 10 microns moving to the sea. Now, again, this doesn't prove, any one case doesn't prove it. It's an accumulation of the evidence. Now, here's another crucial thing that had to be done to make sense out of this. This study is going to look at not the rainfall, the annual rainfall at given locations by itself. It's going to look at the ratio of the precipitation in, let's say, the mountainous areas, either the coastal ranges or the Sierras, downwind of areas, whether they be pristine or polluted, the ratio of their annual rainfall to the annual rainfall in the coastal region. So we're looking at the ratio, and we calculate this ratio every year. So in this case here, using Israel as an example, from 1950 onwards, here you have the value on the plains, upwind of the mountainous areas. You can see there's a tendency for an increase, best fit increase, in the precipitation over that time period in Israel, a lesser increase in the hilly areas. But when you take the ratio and then fit the regression to the ratio, you get that. So you have here you have, this is the ending divided by the starting ratio. And this ratio is really a measure of the orographic factor. That's why it's greater than 1. It just rains more in hilly areas and mountains than it does along the coast. But here you have the ratio here at the beginning was taken from the line early in the period, and the other one that's ending was from the line, not from an individual point, which happened to be 1.19, and what the ratio of the ratios is 0.84. So you have a 16% loss in the orographic factor in the hills east of or east of the area in Tel Aviv and that general area. The p-value on the regression is 0.0006. So it's a very significant regression to those double ratios. Likewise, Los Angeles versus Arrowhead. Again, you've got a slight indication. This is over since 1940 of increase in the plains area of Los Angeles. Maybe a slight increase in Lake Arrowhead, but when you take the ratio, fit a curve to the ratios, you actually have a 16% loss, p-value 0.03. So this is, again, this doesn't prove anything by itself, but when you look at the ratios, this is how you get at it. So this allows you, therefore, in a state that apparently has benefited from a long-term increase in precipitation, allows you to look at the effect on the mountain precipitation by looking at its relationship to that at the coast. So we'll go up and down through the state. Like I said, there's hundreds of these things I could show you. We'll start up here in the north, the relationship of Fort Bragg to Bowman and Mineral. Notice the ratio ending to starting double ratio was 1 and 1.07 at Bowman. So there hasn't been any loss in that part of the Sierras for any reason. In fact, one ratio is greater than 1.07. Now, what I should say here for completeness, I don't want to get into it. That's another seminar all by itself, is you all understand, of course, that the Sierra Nevadas have been seeded, glaciogenic seeding, for 50 years or more. Some programs are going on continuously, some are intermittent and everything else. So in all of this is the question of, well, what has the seeding done to the precipitation in relation to the pollution? Now, some might say right now, aha, well, we got you. It's probably the seeding that's screwed things up. It just hasn't worked the way it was programmed to do. You can't argue that, because in areas downwind of LA where they haven't done any seeding, the ratios are as big or bigger. That is to say, the loss is as big or bigger than there is in the Sierra. So that's not really the reason. And I'm not going to get into it other than to make sure that you understand that confounding these results is the glaciogenic seeding to enhance the snowpack that's been going on. And somebody has, I mean, there's all kinds of things that should be done. That's one of them, is try to separate out the signal from the seeding from the signal that we are claiming is due to the pollution. All right, now here's the relationship with San Francisco to Sacramento, and the ratio, this is the plot here, the ratio is virtually 1. In fact, it is 1. So there's no loss in precipitation from San Francisco to Sacramento. And some say, well, I don't get that. Why? We think these losses come in second-generation clouds that are formed as they begin to ascend the barrier. Clearly, if there's pollution, it would start in San Francisco and continue all the way to Sacramento, and there isn't any loss. But once you climb the barrier to Pacific House on the west slope here, 3,400 feet, the ratio of the double ratios is 0.78, a 22% loss. The correlation between the two stations is 0.93, and the significance of the regression is 0.01. Strongly suggestive of a real relationship. If you look at Merced versus Yosemite, here you don't have as big a loss, 0.93, 7% loss, and the correlation is not quite as good, and the p-value is not as strong. Looking further, Fresno and Giant Forest. Here you've got apparently losing about 22% again. There's the plot, and the p-value is 0.009. Rather likely a relationship. Now, these are the stations on the Sierras where you have just as much precip from rain as you do from snow. We're going to talk about the high Sierra stations momentarily. This is the losses that are taking place in the Sierras here. Now, from Lompoc to Mount Figueroa, you actually have a ratio that's greater than 1. But this is in a more pristine area. As you come south now, I've driven this area here. It's not pristine, but there's much less industry and population here than in the Bay Area and also down in Los Angeles. And it shows in the data. Now when you look at Los Angeles to the San Gabriel and San Bernardino Mountains, you have loss of about 16% in the orographic factor and correlation 0.91. And going farther south as you can go in California, San Diego versus Cuyamaca, if I pronounced that right, it's the biggest loss of all, apparent loss, 27%, but the correlation between the two stations is somewhat degraded. A very, very strong p-value support, 0.0006. So again, looking at its totality, what you see, in its totality, you have the suggestion that in pristine areas you've had no change in the orographic factor. When you move into the highly populated areas, and this is ignorance on my part as to what the effluents are. All we're just relating this to population density, perhaps, in a subjective way. In areas east of San Francisco and east of Los Angeles, San Diego, that's where you have the biggest apparent losses in the orographic factor. That's not. I didn't say we've had the actual decrease in precipitation, because this is counteracted to some extent by a long-term trend in the precipitation. Now, in looking at the ionic content of the precipitation, this is probably more in your area than mine. Looking from the National Atmospheric Deposition Program, we've looked at the ionic content of the precipitation in Sequoia versus Fresno area, and you can see there the mean value in the period 81 to 2002 was 41.3 micrograms equivalent per liter. The trend in the last year has been a slight increase. If you look at Yosemite, Sacramento, you can see the mean is 30.7, and there's been a minuscule trend, a decrease in the past year. Minuscule decrease over the period. This is the value at the end of the last year, in 2002, here, and in a pristine area, last in Ukiah, where the ionic content is about half in their precipitation than it is elsewhere. And these are, in these time periods, the apparent loss of the orographic factor, 24%, Sequoia, Fresno, Yosemite, Sacramento, 22%, 0. No loss at all in the Lassen versus Ukiah. Now let's look at Israel. Same kind of thing. The internal plain versus areas along the coast. You don't have much, but when you look at the internal plain versus Judea hills, here you lost about 15% of the precipitation. They're very strongly correlated, and the p-value is out of sight. Smaller is better, if you will. More zeros there, 0.00, the more significant the result. And so this is a very strong relationship. There's the plot. Again, looking at the ratios. Okay. Likewise, you look at the area there versus the Samaria Hills. You lost 14% orographic factor. Correlation's not as strong, nor is the p-value. Still fairly strong. And then when you look to the south, where there is rather little population, Ramah versus Hebron, the ratio is virtually 1.02. The correlation is 0.87 between the stations. P-value is non-existent. So this is merely consistent, but the relationship is very weak. There just isn't any change in the ratio of coast to mountain to hill precipitation over the period of record in that region, but there is elsewhere. Now, the obvious question is, okay, when does this take place? Because it stands to reason that if you're compromising the ability of the cloud to develop precipitation, it has to be ingested in the aerosols somewhere, somehow. So this is a simplistic way of looking at things based on the temperature off the California coast, which is in the mid to upper 50s this time of year. And what was used was a 700 millibar temperature, about 10,000 feet, of -3 centigrade. So the data for analysis, and there's less to analyze once you start partitioning, divided it at this, with this here. This being when it's warmer in the prefrontal zone, where you have synoptic circulations, large-scale lift. That would be this category. And over here would be in the cold air behind the front. Back in here, where not much rain takes place at the coast, but you can get substantial precipitation in the Sierra from the orographic flows behind cyclones. Here it is schematically. When you look at that, you find indeed, if you look at Cuyamaca versus San Diego, solid here, this is the double ratio plot from the mid-1940s to the present day. You have a loss, in this case, of 34% in the orographic component of precipitation in the cold regime. You've got absolutely no change whatsoever in the other regime. No change at all. Likewise, in Lake Arrowhead versus Los Angeles, here, you're generating these things in a hurry. Now, the dash is comparable to the solid. Just look at the legend here. The cold regime is the dashed, and the warm regime is the solid. It's reversed there. But in the cold regime, you've got a 31% loss in the orographic component at Lake Arrowhead versus Los Angeles. And again, the ratio is actually a little bit greater than 1. In the warm air mass, 1.13. These are smaller samples. The p-values are not as strong. These are merely attempts to understand what is probably going on. I don't think this proves it, but it's consistent with our physical understanding of how clouds work. That when clouds are drawing aerosols from the surface, and this is when you have rather little precipitation on the coast, they're available to be ingested by the cloud and affect the precipitation process. I know we haven't covered everything that human beings are clever, and I'm sure I'm going to get nailed with some interesting questions today. One question that we have anticipated is, well, what if you postulated a climatic change such that over the last century till the present time, the winds change such that the orographic component of the flow is less with time? That would do it. So you're losing precipitation in the mountains not because of pollution, despite the facts of all the physical observation I've shown. If you choose just to focus on the statistics, being clever lawyers now, well, I think that the flows have changed. Ignore the other physics. Well, we looked at that. This is the look at the predicted precipitation in the mountains based on a very simplistic model. Gauge precipitation in the coast times the coefficient. W is the component of the wind speed toward the mountains, the normal component, again times the coefficient. W is the mixing ratio at 850 millibars, and we have a regression constant here. Go through the process and see what you have. Now, what you get now at a given station is, each year, because you've got so many ratios, you're probably swimming in ratios now. Think it differently now. Now, when you look at the ratio of the observed to the predicted rainfall from this crude model. Now, the model may not be accurate. The question is, has it changed? Has the relationship changed over the past century? Here you have Cuyamaca and Lake Arrowhead, both polluted areas, and what you find is that you still, in this case here with a partition sample, you still have deficiencies, not as big, but you still have deficiencies in the measured versus the modeled precipitation. That is to say, the measured is coming out less than the model says you should have had. So the model, this crude model, is saying you should have had more precipitation than you did. And so how does one account for that? If there's not been, if you do take into account the wind flow, you still got a deficiency according to the model, and so you're still left with the only alternative being another cause, a pollution, if you will. Now here we look at a station. I didn't even know where Priest was, to be honest about it, until I looked at it. It does exist in Central California versus the model, and the ratio at Priest over the 50 years is to, this is again, in the starting ratio for observed and modeled precipitation, there's been no change at all. So I don't claim at this 3 minutes I can convince you that there's been no climatic changes. I'd be hard-pressed if I didn't have all the physics, if I didn't have the work of the DRI folks, if I didn't have the satellite work, not here in Israel and in Australia, I'd be on a weaker ground. But all of those say aerosols do bad things to the precipitation. And in California, unlike Israel, Israel's perpetually behind the front. They're different. We here in California can get these big, magnificent cyclones and prefrontal warm fronts. In Israel, if you've ever been there, it's all cold air aloft, and there isn't really ability to partition the way I described it here. But in California, we can do that. Likewise, in Judea Hills, in considering the observed versus predicted, again, you've got a 15% deficiency. So taking the wind into account, the model says you ought to have more rainfall. Where is it? There's 15%. Where is it? Considering the flows over the past 50 years or so, same result. Again, consistency is also important, one area versus another. Now, I did start late, but I promise I'm not going to go over an hour with this thing, and I got started about 10 after, something like that. So I'm on schedule. Don't panic. Nobody's asleep yet, so that's great. I don't know about people on the web, but nobody knows. Now we're going to look at the pollution and snow, because that's another question. Remember, I was looking mainly at lower altitude stations. What would you predict? Let's start thinking. What are you going to predict? What do you think the effect, if there is one, is at colder stations, where the precipitation is almost entirely snow, and you don't get the water from that until the end of the season? What would you predict it to be? Still negative? More negative? Less negative? What would you predict? Well, we looked at that, looking at the snowfall at various stations. And when you look at Fort Bragg versus Mount Lassen, again, the same double ratios, the whole scheme is the same now. Now we're back to the old double ratios of mountain to coast precipitation and fitting the data. He says these are the ratios and fitting the data to it. The ratio there is actually up by 10%. In a pristine area in the mountains, that says you've got 10% more precipitation. Now, my colleagues that have done the cloud seeding are saying, whoopee, Woodley, we love you, because this may be a result of seeding. No pollution up there. How do you explain the fact the ratio has gone up? Well, that would be consistent. I don't think you can make that claim, but it's darn sight better than the other way around. Now, as you work down and look at groups of stations, this is Sacramento versus a whole bevy of stations in here. This is the plot. And you actually have a loss there. Let me see it come up here. Here, I guess it's down here. You have a loss of 8%. It's 7% up here, although, yeah, there it is. 7% loss of Sacramento relative to these crest stations up near the crest of the Sierra. 7% loss, about at least half of what you had before. Down here, it's 8%. Of Fresno versus Kaiser Pass, Emerald Lake, Flute Pass, and Mono Pass, all grouped together. Now you look at, that's just the plot of that. And then we'll look at the east side of the slopes. On the east side of the Sierra Nevada, what do you predict there? That gets really interesting. Want to have some fun, make some predictions there. Well, I'll show you the results, and then I don't want to lie to you. I look like a genius, and I say, oh, this is what I predict, and sure enough, that's what happens, but I already know what happens, so it's not fair. If you guys did it, and we spent some time doing it, we could have some fun, but there isn't time to do that. Ukiah versus Bowman, and Bowman versus Boca, you don't have any change in the east slope precipitation. No change at all. However, when you come farther south into the polluted areas, when you look at Sacramento to, let's see, what station is that? I guess that's Woodford's. No, I'm sorry. This is to Sacramento from San Francisco. Here, when you look at Sacramento versus Woodford's on the east side, you actually have a ratio that's greater than 1.13 on the east side of the Sierras. And you'll find that this is carried all the way through consistently. Not only, I mean, just look at this. It's just truly amazing when you look at it. Look at Glacier. Giant, again, you lost 22% at Giant Forest relative to Fresno, but at Glacier, you gained 20%. So somebody says, well, it's just a wash. Well, these are percentages of different size numbers. That ain't fair. But you gain some on the east side of the Sierra Nevadas, which makes people undoubtedly happy over there. I'm sure if Los Angeles thought this were real, they'd be happy. I understand Los Angeles still gets a lot of water from Mona Lake. Well, this ought to interest them, okay. And again, confounding this is the seeding that's going on. I mean, is the precipitation greater downwind of the Sierra because of the seeding also? That could be possible. But if you believe all this, it means there's more water vapor making it over the divide. That's what all this means. If you lost on the west slope and at the crest, that's water that didn't precipitate. So it stands to reason that you'd have more available to precipitate to the east. But the net effect is you've lost a bundle of water, if you believe the whole thing, even though you've gained some on the east side. Now here's Los Angeles versus Arrowhead. You remember that? Lose 20%. When you look at stations east of the divide, so to speak, east of the mountains, whenever you heard some of these stations, Key Rich and Morongo, the ratio is 1.23 and 1.31. The correlations are somewhat degraded. The p-values are not particularly strong. Again, it's consistent with what we saw elsewhere. If you look in Israel, same sort of thing here. When you look at the Samaria Hills and look downwind of the Samaria Hills in a place called Tuvas, ratio is 1.22. Tamun is 1.19. Again, values that are greater than 1. Different part of the world, the same general kind of result. Here is what we've done schematically, and it's just for illustrative purposes. Please don't think this is the gospel according to Woodley or Rosenfeld or anybody else. But what you have here is our conception that we think embodies the whole statistical aspect of this thing. Remember, you got to remember the physics here as well. But roughly 500 millimeters in the San Francisco area, 450 in Fresno. You climb the hill. Here's the amount you have, 1,100 millimeters in a, let's say, view it as a north-south rectangle along the Sierras on the. So there's a rectangle that goes through the board here along the Sierras. Mean precipitation about 1,100 millimeters. But if you're accepting this, that means you've actually, based on the calculation, you've actually lost 220 millimeters of precipitation on average in that rectangle. Near the crest, up in here, 950 millimeters. You lost 65 millimeters, and then on the east side, 475. But if you believe this 475 is a consequence of realizing additional precipitation downwind of the Sierra Nevadas themselves. So I'm on schedule. Conclusions from our perspective. You may have different perspective. The verdict time in your own head. All the time series from metropolitan areas of California show a decrease in the ratio between the mountain and coastal stations on the years 1950 to 1980. Similar results in Israel. The control or pristine areas don't show any change. They don't show any change in the upwind, the windward slope, the crest, or downwind of the crest. It's all just flat, 1, 1, 1, 1, 1 in those areas in Northern California. Ratio is greater than 1. They were even afraid to put this in the presentation about cloud seeding, so you don't see it here. But for completeness, I owe it to you to at least say that some of these results obviously include the cloud seeding. Now, the decrease we claim is evident only in the cold air masses, where you can adjust the polluted air from the boundary layer. And based on sounding analysis, crude though it be, we don't have any natural trends in the orographic enhancement factor in California or Israel We are, as I stand here today, standing by a 15 to 25% decrease in the orographic rainfall due to air pollution. And this is on annual precipitation now. This is not on the cold days. These numbers, I mean, the percent changes in the cold days is much greater. They're much greater. This is for the annual precipitation. But if this is real, it's obviously being masked. I mean, water is precious. People all in the West fight over water. I know that. But things are not desperate in California, last I checked. And our claim is that we have been a beneficiary of some long-term trends which have given us initial precipitation, unlike the Aussies, where they're hurting, and we're not hurting all that badly right now. But if this is real physics, you've reached your own conclusions. It's something that has to be addressed. It simply must be addressed. Because what if it changes? What if the long-term climatic changes? What if they change? And what if we go into a regime with less water, and we're systematically depriving ourselves of the orographic component that isn't natural to the orography of the state? You get more precipitation in the Sierras because the moist air impinges on the mountains. So what if? So, if I were the great Poobah addressing and saying what we should be doing, and I can have for my 5 minutes of being a Poobah-ness, well, I think, of course, I'd like to do a lot of this work, as would Rosenfeld. So, I mean, that's one of the reasons I'm here, obviously. That's why you talk to people about what you're doing. We need a satellite microphysical survey of California. We have a large number of archived images, albeit in polar orbiters, and one could look with the Rosenfeld methodology, look at the presentations of the clouds and see how often do you see these signatures. Do they occur in the cold regions of cyclones? Can you composite them such you begin to identify the main source of this stuff? Now, you may all know where all this stuff is, in which case you're going to have period to enlighten me. But if you don't, we need to find out. Now, we also need modeling. As I said before, I'm a biggest proponent of modeling. I don't do modeling. I use the stuff. And I will know when I get something realistic as opposed to not realistic. And I can tell you now, some of the stuff that I've seen out of our modeling that I don't take credit for looks very realistic. Here, I envision using MM5 and the explicit microphysical package that we've developed to look at the effect of aerosols on the precipitation. The beauty of models, and I come from a long area of deliberate weather model, not an inadvertent, is once you have a validated model, you can play God in your laboratory, and some modelers think they're God. I mean, they really do. And need people like me who are a pain in the butt to them, but now they're more godly than before, okay? You haven't achieved that status yet. And you can vary the aerosols. You say, okay, well, let's pollute the things up. Let's bring this in, let's do that. You can do anything you darn well please if it bears up, and begin to understand how these aerosols are affecting coalescence and precipitation. The aerosol burden in California. I've got to believe, although I thought Tony disabusing that notion, but I've got to believe you must have measurements, or somebody in California must have systematic measurements of the aerosol burden, specifically C.C.M. in California. The obvious thing to do is take an aircraft with a aerosol package, and a complete package, and fly up and down the state in varied conditions and see what you've got. Are there sources of C.C.M.? I mean, right away you could say, well, you're full of it, because we don't see any C.C.M., but we know differently, and you know differently. Just your gut feeling is, if not other than the diesel traffic in California, which has been increasing, and I should have said earlier, we don't see any changes. When you look at the totality, like the last 100 years or so, it's not getting better. This problem is not getting better. Clearly, the air pollution situation is immeasurably better. As far as I'm concerned, it's nicer in the state. The large particulates aren't there anymore, but I've got to believe the small particulates, the small C.C.M. are still there. I don't know that. Maybe you can tell me when I finally close my mouth for a while. This is another thing. We need to try and address what effect glaciogenic seeding may have had. There's been a large amount of effort put into a program of augment the precipitation of the Sierra, and physically it should help. It should work against this effect and not make it worse. You go through all the physics of it. That doesn't mean that I can say it doesn't, but it should work in a positive way. We need more work of the type that they're doing at DRI. But you got to really give those guys and the men and women credit there. Very painstaking work in a difficult environment, and analyze one or two cases. It just takes an enormous amount of effort. But the work they've done up till now fit just as beautifully as you can imagine. I wasn't aware of their work, to be honest, till recently. And it fits just absolutely beautifully. We need more of it. We need some of that in the Sierra Nevadas. And then we also need to develop relationships between precipitation and runoff. When I talked to the Department of Water Resources yesterday, one of the people there was looking at double mass plots for stream flows. And I think that's important and should be done. But in my view, it can only be done validly if you're looking at streams, coastal and mountain streams, that are directly in alignment with regard to the airflow, upwind and downwind. And secondly, they have to be very high correlated. So just the fact that you generate double mass plots doesn't tell me a darn thing. But that's clearly should be done. So I mean, there's enough work here for an army of people who are inclined to address it. Okay, I'm going to stop here. Would you believe there's more of this presentation? But it's for meteorologists that want to talk about the effect of aerosols on deep convection. Missouri, East Texas, and everything else. It doesn't concern you here. I have some model results and everything else. But I'm right on schedule here, and it's time for me to stop because I think that I give you our picture of what we think is going on, not only just here in California, but in Israel and also in Australia. And the Aussies are paying for it dearly, and sometime, some way, they're going to mend their ways and look at this more carefully. Thank you very much. Thank you for the invitation to talk. It's been a pleasure speaking to you today.
Thank you very much, Bill. That was an excellent talk, and definitely a lot to think about. We have time for a few questions, both from the people in the room, and if folks out on the web have emailed in questions or can get cracking and do that right away, we can probably handle a few of those as well. I'd like to start off with one question, not to pick too heavily on modelers, but on a global scale, there is a big issue here. The paper you mentioned by Ramanathan in Science predicts a general slowing of the hydrologic cycle due to black carbon effects and the shading of the oceans and reduced evaporation and that sort of thing. Obviously, the dynamics that you're seeing from air pollution here are a more subtle kind of effect. And then there's a third version of this story that's told by the work of Hansen and Manon, who are claiming that soot is actually causing enhanced near-field precipitation and decreased far-field precipitation in the Asian monsoon. Could you sort of reflect on whether or not those three ideas are compatible with one another?
Well, again, the comments regarding modeling are those results I can validate myself with observations. I always am enormously amused by modelers that look decades or centuries ahead, and nobody's ever going to verify those folks. And that's the ultimate world, to do your research and pontificate, and nobody ever bothers to validate it. Now, in terms of the effect of soot, for example, it depends on what the makeup of the soot is. It's true that if the pollutant is cloud condensation nuclei in larger sizes, it actually is beneficial to the precipitation. So that aspect I would agree with. I have to follow the reason to see why it's near field would be increases and far field would be decreases. I don't quite understand that one, but the first part of that makes sense. There's been a resurgence in deliberate weather model of using hygroscopic agents. We know now that from studies of the type I've talked about, that what nature does in polluted parts of the world over the oceans is cleans up our act, literally. because the salt from evaporating sea spray gets ingested in these polluted air masses moving out, and you enhance the coalescence, enhance the precipitation. This goes on and on and on, and eventually nature cleans up a polluted air mass, central Indian Ocean, that's as pristine as you could ever imagine. How hygroscopic got started is somebody observed in South Africa, flying around in an airplane, cloud physics airplane, that the precipitation was dramatically enhanced over paper mills. I don't know how many paper mills there are around here in California and Oregon, but in that particular environment, sure enough, the paper mills enhance precipitation. The pollution from those paper mills, you get more precipitation, but you've got large cloud condensation nuclei. So that's as best I can do on the modeling at this point.
Maybe when we study the impact of the aerosol, maybe we need to look at the chemistry of the aerosol. For example, sulfate or some organic, they have a tendency to absorb water and they grow in large, so that would be, more efficient way, to create enhance the cloud, formation and end up with precipitation, especially when we are dealing with the shallow convective type of the, cloud, that we don't have that much problem with the availability of the moisture, and you have some kind of the compound that like to absorb the water and grow in size and be more efficient cloud condensation nuclei. So I think that the chemistry of the aerosol should be also.
I couldn't agree with you more. Absolutely, I couldn't agree with you more. As I said here, I don't know what your research interests are, but there's in that shopping list I've got there are some basic questions that need to be addressed, and one of which, of course, is the makeup of the aerosols. How many are there? What's their chemical makeup? And where is it coming from? And so, yeah, I agree totally with what you said.
I think you've seen the temperature data from, I think, like about 200 stations in California, which basically show that there's since, if you look at since 1950 and then since 1980, there's been a substantial change upward in temperature. And at alpine locations, that change in temperature, which obviously may be due to what we call climate change, is far more evident than it is at locations in the alluvial plains. Is that not an interference or a confounding effect on the observations that you're making? Thank you.
If the convection, first of all, if the changes were substantial, several degrees, I'd be concerned. But in an instance here where we're looking at precipitation that's being driven primarily by the orography, unless you've had a big change in the temperatures, big changes, I wouldn't. It's a factor, but I wouldn't consider it to be a major factor in this.
I don't work in the air arena, so this may be one of those questions outside the box. But if from your data it looks like that there's less precipitation, and if that's caused by this smaller C.C.M, then are the clouds made up of a lot of small particles and they're actually getting larger clouds? Or are we just not making as big clouds?
When you talk about California, you're not so much talking about the depth of the cloud, because you have thermal stratification that doesn't allow you to have very deep clouds, particularly in the lee fronts in the upper trough regions. So what you have, therefore, are clouds that are essentially the same size regardless, but in the polluted case, you have a cloud, and we know this by measurement. We've actually made measurements in polluted clouds. You have very tiny drops. And so nature, I mean, let's face it, it's easy. The simple thing is you condense water and you get some of it to the ground. That's precipitation. How do you do that? Well, the more quickly you can get the particles to grow to large sizes, the more quickly you're going to have precipitation. You'll have, when it gets cold enough, you'll have ice formation and riming. So in California, in the polluted areas, what you have are clouds that have drops that are so small in general, they're not able to grow and accrete one another, coalesce with one another to give large size drops and particles that can fall to the earth as precipitation. So it compromises that process, is what the pollution does. And this is not guesswork. We see that observationally and also with models That's a gimme. That's a gimme. That's what the pollution does in general, both observationally and with models. It just ruins the precipitation forming process, and you can see it. I answer your question? I'm not sure I did.
Well, I mean, when you're showing a 7 to 10% reduction in precipitation, and that water has to go somewhere.
That's correct.
And so it either stays in the clouds, you either have either denser clouds or more clouds, or it never forms in the clouds.
Well, in the case of the Sierra, what you have, because you have lesser precipitation in the polluted areas, is once you get to the lee of the Sierra, there's subsidence, and the clouds will evaporate. That was very dramatic in driving from Reno to Sacramento earlier in December. So what happens is that water evaporates. So what you do, therefore, as a consequence of the pollution, you are transporting more water vapor downwind of the Sierra Nevadas, which should make Nevada very happy, and other people downwind. But if you could say, hey, it's our God-given right, we have mountains, and the orographic factor should be 3, and we aren't getting 3, we're getting 2.5, or whatever it is. That's our water. I mean, this gets into a delicious area of legalities and everything else. So you can just sit there and grin, think we got problems. Because if this happens, what the pollution is doing is beneficial to Nevada, unless there's enough pollution that comes down and goes over in Nevada, in which case they don't precipitate there either. So who knows where this all ends? But that's. And you do see here, I don't see how. How could all these things conspire to give these results? Here in Northern California, Southern California, and Israel, and everything else, you got enhanced precipitation downwind of the barriers. You have small losses, relative small losses at the crest, and big losses in the upwind areas. And it goes. You see it over and over again. There's hundreds of plots I could have shown you. Same thing happens. So that's probably real. So to answer your question is, the water stays in the cloud, then evaporates, and then is in the atmosphere, available, presumably, to be used elsewhere.
Okay, well, we appear to have answered most of the questions, and I'm sure there will be some folks who will want to catch you one-on-one after the talk. Again, I'd like to thank Dr. Woodley very much for coming to talk with us, and thank all of you on the net and all of you here for joining us. And this concludes this seminar. Thank you.
Thank you.